Often we define a number of random variables on the same probability space, and we want to know certain things about their distribution together. In other words, their joint distribution. In that case, we could talk about a random vector, which is basically a number of random variables defined on the same probability space. And this description makes it more clear, in fact, why we started with the description of a sample space when all we wanted to do was to talk about random variables. Because we can only talk about their joint distributions. So, for example, the joint cumulative distribution functions of these random variables by going back to the sample space description and understanding this probability. So if we write the probability that x1 is bigger than t1, x2 is bigger than t2, xn is bigger than tn. This would be the complementary CDF of the joint complementary CDF, and we can compute this probability, and this would simply mean the probability of the outcomes W in the sample space for which, you know, x1 of W is bigger than t1, etc. xn of W bigger than tn. So basically, this is the complementary CDF which is 1 minus the CDF, right? Right. Now, in the case when this CDF is differentiable, we can talk about a joint probability density function for the random variables. So we would define the joint CDF, joint PDF. As a function of variables x1 through script x1 through script xn as the nth derivative of the CDF with respect to all these variables. And this is known as the joint PDF of x1 through xn. Right. Now, sometimes we have a collection of independent random variables, and it is easy to check this from the CDF or the PDF. Okay, so x1 through xn are independent if and only if the cumulative, and I use vector notation here, the cumulative distribution function factorizes into the product of individual or marginal CDFs of the individual random variables for all values x1 through xn in the real numbers. Okay, so this should be satisfied for all possible real vectors x1 through xn. Right. Later on, we will talk about the case when the random variables are correlated. But in order to analyze that, in order to define and talk about those things, we will first need the concepts of expectation and variance. A stochastic process is essentially an infinite collection of random variables defined on a common probability space. And in the next lecture, we will talk about a stochastic process beginning with a discrete stochastic process.